So where we've seen that expression of SVS divided by V before, it's omega. You may recall it was called the elasticity of the option. Elasticity was the ratio of the percentage change in the option price divided by the percentage change in the stock price. And we saw that even though a typical option might have a delta of around a half, we saw examples where the elasticity of a call option could be 4 or 5, namely that for every percentage point that the stock price changes, the call option might change 4 or 5 percentage points. That's what elasticity is. So what we find is that the variability, the volatility, I should say, the volatility of the option is elasticity times the volatility of the stock. So elasticity is like a multiplier for volatility. It takes stock volatility, and the elasticity is a multiplier that gives us the option volatility. Now, we're going to use a result that we studied earlier, and that is one connection between the process for the option and the process for the stock is they have the same DZ term. Anytime you see that, the first thing that should come to mind is if they have the same DZ term, they're perfectly correlated. If they're perfectly correlated, they must have the same Sharpe ratio. It's a 1, 2, 3 kind of deduction. Same DZ term, that's what Ito's lemma says. Ito's lemma says the derivative security has the same DZ term as the stock. That implies they have the same Sharpe ratio because they're perfectly correlated. So we can now say that the Sharpe ratio of the option, which is the expression alpha option minus R divided by sigma option, that's the formula for the Sharpe ratio for the option, that must equal the Sharpe ratio for the stock, which we know. The Sharpe ratio for the stock is alpha minus R over sigma. Another way of rewriting this equation that the Sharpe ratios are equal is by a substitution for a sigma option. That we can substitute the formula for sigma option into there and solve for alpha of the option. And what we find from this is that the alpha of the option must satisfy this formula. That's important because now what we can do is say we have two expressions for the expected return on the option. One we got from Ito's lemma here. One expression is that alpha option comes directly from the Ito lemma applied to the option. And secondly, we have an expression for alpha option. Let me page back, sorry. Secondly, we derive that we have an expression for alpha option in terms of other parameters, in particular the alpha of the stock and the risk-free rate. So what we're going to do is equate these two expressions for the return on the option, and that's what we do here. And if we simply multiply it out, do a little bit of algebra, miraculously we'll find that the alpha terms cancel. And what is left is the Black-Scholes differential equation. In other words, we can try to force a differential equation to reflect alpha, but we can only do that notationally. That's what we started with. Once we think through the idea that, well, wait a minute, the alpha on the stock and alpha on the option are related because their Sharpe ratios are related, and we make the appropriate substitutions, we find that what looked like a differential equation that ought to reflect alpha, ultimately the alphas cancel because we have an additional expression of alpha that comes from the Sharpe ratio analysis. And finally, when we're done, we end up with the Black-Scholes differential equation. And this is a similar analysis that we did at the end of an earlier module whereby we attempted to price options on a binomial lattice, but using the real return on the stock rather than the risk-free return. And to do so, we had to change the probabilities on the lattice. And we found that after all that work, when everything was accounted for, we ended up with the same price as we did with the risk-neutral probabilities implied by the DZ in Ito process, as well as the risk-free rate.